IT is going to be here. No one really sends in like IT service stuff for computers. They never know when a computer runs. Anyways, this is where we left off. Like we were making sure you have this typed in and that it actually runs. So I did ask, what does each line do? So let's, just lay it out, right? So set.seed, what's the point of that?
Right.
Yep. So it ensures that we all get the same number. So even though we're running random number generator, right? We all want to work with the same exact number, so we can set the seed. It starts it here in 2015, and then it goes in a very predictable manner. All right. So this is line 1. All right. Line 2, 3, and 4. You're all generating random numbers. So what we are going to do is, for line 2, we are randomly drawing 10 numbers from a normal distribution of mean 15, or normal distribution with mean 15 and SD 3. And numbers are rounded to 0.1 and saved as the vector AB1. All right, so that's what our second line did. So our norm is going to random drawing from a normal distribution. The normal distribution that we're drawing it from has a mean of 15, standard deviation of 3. We're going to round those numbers. So the way that R does in the nesting, all right, it's going to operate first inside the parentheses. So it does that R norm, generates those numbers, and then we're going to round each of those numbers to the nearest decimal place, the tenths. And then we save it as AB1. Line 3, randomly draw 10 numbers from a chi-square distribution that has 4 degrees of freedom. Again, don't worry if we don't understand degrees of freedom, we will talk about those. Numbers are rounded to whole digits and saved as vector AB2. That down. Together. And then line 4. Okay. Randomly draw 100 numbers from a Poisson distribution with a mean equals 1.5. So randomly draw 100 numbers from a Poisson distribution with a mean of 1.5 and save it as the vector AB. So AB1, AB2, AB3. So that's what these lines are doing. You'll have something like this on the exam where I'll give you a code and say, okay, just verbalize it. Tell me what this is doing. We want to be complete. This is what each line is doing. And I'll leave that up here. So all of our numbers should be the same. That's a good thing. If you saw something like R chi-square and you didn't know what this was, if you didn't know what this was, how could you find it? Find that information? Yeah, look at the help file. All right. Remember how to do that? A couple different ways. I would just go over to help, make sure we're in the help tab, and arc chi-squared. There it is, pops right up and click it. The non-central chi-squared distribution. So, tells you about it, tells you how to calculate it, tells you what you have to give it, and then write in the value, arc chi-squared generates random deviates. So, and at the bottom, that also gives some examples on like how you could use it. We probably won't. I'll use the chi-square distribution to generate random data because it's non-normal and it's apparently non-normal. So, you know, when we use it, that's why we're using it. All right. So we have all these data. We have it. So first descriptors, we're going to start with location, which is our measure of central tendency. So the first measure of central tendency, and probably the most common type of central tendency, is the arithmetic mean. All right. This is what we say is the average or the mean. We're talking about the arithmetic mean. All right. This represents the center of all of our observations. The easiest way to think about it and distinguish it from the rest is if you take the histogram of all of our values and you balance it, that histogram on a pencil, that balance point represents the arithmetic mean. All right. So if you're on a bell curve, that balance point will be right in the middle. If we are skewed a little bit, so if we are skewed something like that, with a heavy tail, all right, it's not at the peak. Our balance point's going to probably be someplace right there. Because again, we're trying to balance the histogram, the large values and the small values. All right. So we calculate the mean by taking the sum of all of our values and dividing it by the sample size. That is what this equation is telling us. It's the sum of our values divided by the sample size. So in this example, we have these values, all right, a vector of values. We add up all of the data points, all of them, so 5 plus 6 plus 6 plus 7 plus 7 plus 8 plus 9 plus 12, and you divide it by 9, because we have 9 values. That is our arithmetic mean. Hopefully you've all calculated averages before, right? All right. By convention, when you calculate the means, we typically add one more digit to the average. So if we're calculating an average of these numbers, whatever that is, we'll go to the tenths place. That's just by convention. One more digit than the raw data. Are we going to calculate it by hand? Nope. We're going to show you how we can do it in R. All right, so the long way is this way, where we actually type in the sum. We use the function sum to calculate the sum of all of those numbers. And then we divide it by the length. All right, so first up, what I'm going to do is make a vector. I have it called as x here. That's a bad number. I'm going to change that actually. X1. I'm just going to call it x1, the vector. All right, and then you've got these two codes. So first one, to convert this mathematical expression to R, what we would do is use the function sum. So sum will take the sum of all of the values in a numeric vector, x. All right, and this na.rm is there because if we have any missing data points, we want to take those out before we calculate the sum. And then we're going to divide it by the sample size. Now, we can't just do length. So length of a vector tells us how many rows are in that vector. All right, it tells us how many rows we have. That's not what we're interested in. If you have a missing data point, it still has a row in there, but the data point is missing. So if we use length, it's going to count that missing data, and our average will be wrong. So what we use is this, which is called subscript notation. So the brackets is a subscript notation, but it's saying is we're going to take the vector, and we want all of the items in that vector to be included, with the exception of those where our data points are missing. So that's our is NA. All right, so is NA. You'll see this in a function that I give you, that I demonstrate how to make a function. You'll see this type of notation here. All right, so this is a lot of typing, right? A lot of typing, a lot of shifts to get things to appear correctly, which slows us down. Fortunately, R has a function called mean that will do this same thing for us. It does basically this. So we take mean, we give it the numeric vector, and we let it calculate. Now, this na.rm is important because, again, it's going to remove missing values before it calculates the mean. If you didn't do that, then you'll get an error. You'll get an error, all right? So, for example, let's work with this x1 just as a demonstration. All right. So I'm going to start. We are dealing with central tendency. Arithmetic mean. The function that we'll use is mean of x na.rm equals t. Right. Mean of vector x after removing missing values. All right. So I'm going to create this vector x1. I'm going to make that, and then all I have to do is do x1, na.rm equals t, and when I run this, you will see that it calculates 7.5, which is exactly the same as if I pulled out my calculator here. It's solar, so I need light, and do 5 plus 6 plus 6 plus 7 plus 7 plus 8 plus 9 plus 12 equals, and 60 divided by 9 is 5 plus 6 plus 8 plus 7 plus 8. Oh, we've got 8 values there. Divided by 8, I get 7.5. 5, 6, 6, 7, 7, 8. I get 7.5. Really easy. Really easy, right? All right. Now, calculate the averages of these three vectors that we made. I'm going to double check that these are the numbers that I get, but we just want to confirm that you calculated the same one. All right, did you get it? Mine came out the same. Yep. Now, the nice thing is that the default, or that if you have a vector without any missing data, you don't need the na.rm. You don't have it, there's no missing data in our vectors. So I can just use mean, and that's it, it calculates it. But I did want to put in what happens if we have missing data, so that you can see the error message that we'll get. So I took x2, which is the same vector as I used for this demonstration up here, and I put in a missing number, NA. Okay. If I run this, I get NA. It's missing. Right. If we fail to use NA.rm equals t, and there is at least one missing data point, R will return NA. All right, so we fix that then. If that happens to you, you calculate the mean and say, why do I get NA? Go back, NA.rm equals t. When we run it, you'll see that we now get 7.5, which is what we should get. Still has an NA because we have a missing data point. NA.rm equals t, removes it. And you might ask, why wouldn't we just go ahead and remove the missing data before we input our data file into R? And you can, I mean, you could do that, but normally in research you'll have a missing data point that doesn't necessarily mean you lose that entire individual. So, I think the mammalogy class has a lab across the hall. If they're looking at skulls and we measure, let's say, canine, okay? We'll have a left canine and we'll have a right canine. So each skull represents a sample, and we're interested in just using those measures to help us identify or to distinguish a new species. It's possible that one of those teeth is missing. So why should we eliminate the entire skull from our data set when we only are lacking one tooth measurement? So generally, that's why we leave the NAs in our data set. Pretty easy. Weighted averages basically are used to calculate average of averages. That's the best way I can say it. All right, so our mean is an average. The arithmetic mean is an average, and it assigns equal weighting to each of our data points. That could be true when your data points are individual values. These are individual data points. But let's say that we are looking at averages, class averages, and we're comparing our class average on exam 1 of this class to last year's class and the year before that class, right? And we're looking for like an overall average. Would it make a whole lot of sense to have the same weighting for each of our classes? Probably not. We have, I think, 16 or 17 students in this class. I think last year we had 22 students. Another year we may have only had 11 or 12 students. All right, so what you have when you're looking at like overall average is we want to account for those differences in class sizes. This is a weighted average. All right, so the weighted average looks something like this. Now you're going to see this equation again because we can use it to calculate averages from frequency tables. And you'll learn how to take frequency tables to convert it to a vector, take a vector, convert it to a frequency table, and so forth. It's kind of an interesting or good skill to have. So what this is you take each of your x values, each of your data points, all right, and you multiply it by the weight, by the weighting. All right, that gives you your sum. All right, so each x multiplied by its weight, you add them all up, and then you divide it by the sum of the weights. R also has a function that does this for us, and it's weighted.mean. So weighted.mean takes a vector x, takes a vector of weights, so each of our points has a weighting attached to it, and then it also has this NA.rm equals t, because if we have any missing values, we want to remove those before we try to calculate it. All right? So let's do an example before we get to our table. So this is weighted mean. So our function is weighted dot mean. We're going to give it a vector of x, a vector w, na.rm equals t. And again, if you don't have any missing data, you can leave that na.rm off. So x is a vector of data points. W is a vector of weights. All right, so here's our example. Let's do exam 1 is 20% of our grade. Exam 2 is 30%. No, yeah, 30%. Exam 3 is 30%. 360. We'll do this. We'll go 50. We'll go 25 is exam 1. Exam 4, actually final. This is probably the classic time you would see it. I think that's 50. All right, so these are the weights. Exam 1 weight. Exam 2 weight. Exam 3 weight. Final exam weight is 15%. So, get up there. Yep. Total weight's going to be 100%. So we'll just make up some scores. So exam scores, we'll say we had 90% on the first exam. Let's do 88 on the second exam. Let's do let's really bomb third exam, and then let's do a 95 for that last exam. Okay, and then I'm going to put in the weights, and we are going to use percentage. So 0.25, 0.25 for the first one. 0.3 for the second, 0.3 for the third, and 0.15 for the last. All right, so you can use this in any of your classes. All right, so I'm going to run this. We have them. And just note this. If I do mean of the exams, we get 84.5. But note that I put this is the wrong way to do it because we have different weights for each exam. All right, final exam's worth the least. It's 15%. Yet, when we take the mean of this, it assigns equal weighting to all of the exams. All right, the proper way to use is this weighted dot mean function, where the values that we're going to calculate, our average, will be the exams, and then our weights. And I don't have missing data, so I don't really need the na.rm equals t, but I'm going to put it in there because you're learning. So now when I run it, and I run the chunk, you can see that our actual exam average is lower. It's 82.65. That would be the course grade. Because it gave different weights to each of these. So yeah, 65 really hurt because that was a 30% exam. Okay. And our final was only worth half as much as exams 2. So makes sense for the weighted means? All right. We'll get this back up. Most likely scenario, well, other than getting these exams, and you just look at the syllabus. This is how I make my syllabus, so you can read those percentages. Other way to use it is a frequency table. All right, so we're going to work with AV3. AV3 is discrete data. It's from a Poisson distribution. So if ragweed are randomly distributed across the landscape, they should follow a Poisson distribution. All right, so go ahead and make this frequency table. Not like make it in Excel, but generate a frequency table for in R. All right. Take 5 minutes to go back and look at how to do that. Talked about it last. How did you make the table? Table, right? Table. All right, so how do we make a frequency table? Table. All right, and we get this. Now, this is good, because what you could do is make a comparison. So if I look at AV3, that's our vector. This is our vector. So it's got 2, 1, 1, 3, 0, 1, 0, 1, 2, 1, 1, 1. If you remember, I said we took grids, we put them out in the grass, and we counted how many ragweed were in that grid. So each row represented a new grid that was placed down on the ground, and each of these counts represents how many ragweed were in that grid. So the first grid had 2, the second grid had 1, third grid had 1, and so forth, all right? That's what our vector looks like. If we wanted to calculate the average, we can. We just do mean of AV3, and that's what we get. But this is normally displayed as a frequency table. So if we do table AV3, it says we have 18 zeros in our data set. We have 33 ones, 27 twos, 16 threes, 2 fours, and 4 fives. All right? So our x values are the grid that had the count of how many ragweed, not the count, it's the count of ragweed in each of the grids. So it's our vectors, all of our x's are either 0, 1, 2, 3, 4, and 5. And then our weighting is the actual count of how many grids actually had that number of ragweed. All right, so we've got our vector of x's, which is 0s to 5. We have our vector of counts. What we can then do is pass those numbers as vectors right to the weighted mean function. So here I've got weighted.mean. Here's our vector of x's. So we got 0, 1, 2, 3, 4, 5. All right. We have our vector of weights. And again, remember, you make a vector using lowercase c. Okay. There's a vector of weights. You don't have missing data, so I'm going to leave na.rm equals t off. And then I'm going to run it. And what I want you to see is that if we have a frequency table, we use weighted.mean to calculate the average. If we have the raw vector, you can get the same answer just by doing mean of AV3. So you get the same counts. And we're going to be doing this. All right. need to move the camera, and I will zoom in. I wish this board was just like a little longer. All right, so I do say, how do we do this by hand? It's actually fairly easy. There we go. There we go. All right, so with our table, we have our x's, we have our frequencies. So 0, 1, 2, 3, 4, and 5. We have our table of frequencies, 18, 33, 27, 16, 2, and 4. All right. So we need a weighted average, x times f, multiply across. Multiply across, we add up this column. That is the sum of our frequencies times the x's. All right. Which is what?
The right side's 23.
What's that?
The right side's 23 compared to.
Okay. Pull out my calculator.
Yeah.
This is the only downside with the solar. 163. Oh, that makes sense. 100 data points. 163. That's our sum of our fx. This column here, sum of the f's. We had 100 data grids. So then our average then is that 163 over 100. Really, again, can't be easier. I mean, it could be. Really easy. You use this, the weighted means, when we actually are assigning, assigning different weights to each of our values. Frequency tables is one example of when we would use weighted means. All right, so other means. Yeah, other means exist. We've got geometric mean, we have a harmonic mean. All right, geometric mean is basically the product rooted based on our sample sizes. Harmonic mean is basically inverses, like some of the inverses. Inverse of like some of the inverse. When would we do these? Geometric mean would be the ones that you are most likely to encounter outside of the arithmetic mean. We would use geometric mean anytime our data is on the exponential scale. All right. When you have exponential scales, when you use serial dilutions. All right. So if you're in microlab or virus lab and you are doing 10-fold serial dilutions or 2-fold serial dilutions, that fold, 2-fold, 10-fold, puts you on the exponential scale. So you're going to get very large numbers, very large spans of numbers that differ on several orders of magnitude. So you may have a value of 100 and then you may have a value of 10,000. Those are two different scales. Geometric means help to balance those out. That's our sizes that span several orders of magnitude. Also apply to that. Population growth rates. So those that have had ecology, when we talk about R, the intrinsic rate of growth, if you estimate that for every year and then try to calculate an average, what you should be using is the geometric mean because our R's, the R's are on exponential scale. All right, the sole function of this is to try to normalize our range, to try to compress the range so that our averages are more reflective of the underlying data. The harmonic mean, unless you go into physics, probably won't use it. All right. We use a harmonic mean when we're calculating averages of rates. So sure you've all have seen that problem or remember the problem that they say it's on the SAT. An elephant is walking a rectangle, and it travels 5 miles an hour first for X number of miles, or for X amount of time, and then travels 10 miles an hour on this span. If you ask for the average speed, you would use a harmonic mean. Are we going to do that? No, we won't. We're not gonna work with it because we hardly ever use it. And as far as the geometric mean, yeah, you could encounter it, but normally when you work on serial dilutions, where you use geometric means, you're going to take the log of those values and you're going to be plotting on the log scale. So then when you take the averages of the logs, that is going to be our geometric mean. So, yeah, that's basically why we're not going to cover these. You are expected to know when you might use them. So if I say we have different rates, enzyme rates of reactions, and we want to know the overall average for a batch of experiments, well, that's here, rates. That's our harmonic mean. Or if we do serial dilutions, or if I give you numbers, it's like these are a vector of numbers, what type of mean would you use? Geometric, harmonic, or average? Or arithmetic, geometric, or harmonic? All right, relationships. Arithmetic tends to be the largest mean, followed by geometric and then the harmonic mean. FYI. That's all you need. Any questions on the means? We're going to focus on the arithmetic. That's what we're going to do. All right, the other type of central tendency is the median. The median represents the 50% point. So whatever the median is, half of our data points lie below it, half of the data points lie above it. All right? How we calculate it could vary. I'm going to tell you that. It can vary. All right? R uses has a function called median that will do it for us. However, I'm going to show you how to do it by hand because it's a useful skill. The trick, though, comes down to how do we handle even number of items versus odd number of items? How do we handle duplicates? All right, where do they go? How do you once you have a median, should that median be included in one batch in the 50%? Or should we be in the lower group or the higher group? There's a lot of things, a lot of different people have come up with multiple ways to do a median. I'm going to show you how to do it by hand, and I'm going to say, do this. This makes it easy, and we don't have to worry about it. All right, so median, how do we access the median in R? It's just median. That's all it is. Pull up my R markdown. Median is the halfway point in our data set. The function that we'll use to calculate medians of vectors is median x, and again, we have na.rm equals t to remove missing data points. And x here is a numeric vector, so it won't work with lists. All right. So we had that vector x1 that I made. If I do median x1 and hit go, it tells me 7 is the median. So goes out. Let me move this. We have x1. We know it's 7. How could we do it by hand? up so I can see my x1 value. Best way to do it, you line up the values in order, smallest to largest. So our vector was 5, 6, 6, 7, 7, 8, 9, and 12. Two values. Our 50% point, right there. Right, that's our 50% point. We have 4 values there. We have 4 values here. Now the question is, what happens when we're between a point? Well, when we're between the point, we take the average of these 2 values. So that's our median. All right. And that's when we calculate median. Anytime we do it by hand like this, R will give us the exact same number. The same number that we would calculate by hand. All right. The other thing that's related, oops, there it is. The other values that are related to the median are quartiles and quantiles. All right. So the quartiles are the first quarter, second quarter, third quarter of our data set. All right. Our second quarter is the median. Our second quartile is the median of our vector. The first quartile would be the point where 25% of our values are to the left of it, 75 are to the right. Our third quartile is the 75% point. So 75% of our values lie below it, 25 above it. All right. This is also one that has different ways to calculate it. As I said, R has 9 ways to calculate these quartiles, and it's based on what happens if you're in between numbers, what happens if you have duplicates, and so forth. All right. So what I'm going to suggest is just doing it how I would do it, other than let R doing it for you. If you need to calculate it by hand, what I suggest doing is taking your data set, finding the median, and then once you find the median, you take the median of our upper and lower blocks. This 6 plus 6 over 2, which is 6, represents our first quartile. This one, again, 8 plus 9 over 2, 8.5. 8.5, that represents our third quartile. These are important ranges because once we start working with medians, we don't, our measure of dispersion is this interquartile range, which is the first and the third quartiles. That's how I would recommend doing it by hand. What about quantile? Quantile is the percentage point. So the 25th quantile, or 25th percentile, is our first quartile. 50th percentile, 50th quantile is our median. 75th percentile, 75th quantile is our third quartile. All right. Not terribly bad. Fortunately for us, R has a function called quantile that will calculate these different breaks for us. Now, what we want to do is always ask R to report the common ones, which would be the 25th, the 50, and the 75. All right, and with our function, we actually have to give it the percentages, and the percentages would be in decimal format. So, just to demonstrate with this EX1, so median X1, and then our quantiles and quartiles. All right, so we would do quantile, and we would do our vector x1 And then we'd specify the probabilities. So I'm going to do 0.25, 0.5, and 0.75. And that's going to give me the first, second, and third quartiles. And you notice that we do get slightly different values with quantile, right? Than what we would have done by hand. If we look at the help file of our quantile, there's this option for type 7. These 9 types are all different ways to calculate your quantile. So if you are working in an old version of SAS, probably use the type 3. This one's used. Type 6 is the default in SPSS. So if you're in nursing or in psychology and you learn how to do medians and quantiles in SPSS, to get R to match those values, you have to switch to type 6. All right. The default is type 7. Yeah. So if you wanted to, you can go read read this paper. You can read all about this if you're curious. We're just going to do the default. Let R do it. I can see that you know the function. I can see that you're getting answers, and you can interpret them. Questions? All right, so how do we do the probs? Could be tricky. We did this as my example. I use this one. So it's going to give us a first quartile, the median, and the third quartile. Those are typically the ones that we want. All right. The default, if we left off probs, is to do those 3 along with the 0 and the 1. So basically the minimum, maximum values. The other common one is this, 0.025 and 0.975. You're going to see this pop up a lot during this class. This represents 2.5% to the left, 2.5% to the right, which means what percentage of points lies between these values? 95%. All right, so if we do randomized drawings, randomization tests, and we're trying to get asymmetrical curves, error bars, we often use 95% confidence intervals. This would give us a 95% confidence interval. If we're working and looking at a 5% cutoff, so p-value of 0.05 seems to be our magic cutoff, we can specify where that cutoff is at 0.05 or 0.95. 0.05 if we want 5% to the left, we'd use 0.95 if we want 5% to the right. All right, and you'll see these again. But I put these in here so that you have them in your notes. All right, so here's 2 examples, give you a little bit more practice. Here's DAT1 and DAT2. What I do say, make a vector of these values, call it DAT1 and DAT2, and then calculate the median, the quartiles, and 95%. And then for DAT2, do the median, the 2.5%, and 97.5%. Just to give you a little bit more practice entering these probs or specifying the probs correctly. get it? Still working? Uh-oh. Still working? You don't need median by default. Yeah, just median. I think it will ultimately go to that function, but we'll try to avoid if you run that same ones. Yeah, so then we want to use the quantile function. The quantile would be used to get your percentages. So I made my vectors. So I make my DAT1 and DAT2 vectors. All right, and then for DAT1, we're going to calculate the median, the quartiles, and the 95th quantile, 95th percentile for DAT1. All right. So I can calculate the median. I could use median, no problem. But I know the median is the 50th percentile. Right? It's the 50th percentile. So what I'm going to use is the probs, or use quantile function, and then specify my vector of probabilities. So I want my quartiles. So that's 0.25, 0.5, and 0.75. So the first quartile, second quartile, and third quartile. I'm going to get those. The second quartile is the median, so we have that. And then I want the 95th quartile, so I will use 0.95. And when I run it, I get this output. So my first quartile, the median, third quartile, and that's our 95th quantile. You don't have to put them in order from largest to smallest. So for DAT2, I asked for the median, then the 2.5 and the 97.5 quantiles. So just to kind of demonstrate that, I said, okay, I want the quantile of this DAT2 vector, the probs. First one I want is the median, so I want the 0.5. Then I want the 0.025 and the 0.975. And it'll give me the output just as I asked for. Yep. Different numbers? Or is it work? Hold on. Probs. After the equal sign, do your C, lowercase c, and then put those numbers in parentheses. You'll need one more. There you go. All right. Did you get this? Not terrible? All right. When do we use it? As you're going to learn, when we violate normality, we can't use classical tests, which probably means the mean, arithmetic mean, isn't going to be the best descriptor of our location of central tendency. So normally, if you have skewed data or highly asymmetric distributions, median more accurately represents the central location. So you're going to see it, salaries, home prices, you hear it being reported as median. Anytime you hear average being reported in the news, send up your radar. Something's not right because those numbers are highly skewed. All right, they should be reporting median. You'll hear it when the media is trying to make a point. All right, if they say, oh my goodness, look at St. Angelo home prices, they're so expensive. They say the average home price is $500,000. Now, a median home price might only be $125,000 because that represents more of your like 50% point, right? It just happens that we've got, let's say, $10 million homes. Those 5 $10 million homes that bring up the average. All right, so anytime we have highly skewed asymmetric data, we usually use medians and then our interquartile ranges to represent our dispersion. The other time we might do it is if we have limited time or resources. So if we can't collect all possibilities, like do all possible dilutions, then what we could do is we skip levels and then we infer what would happen between it. So an LD50, who knows what an LD50 is? lethal dose 50%. So it's a dose that'll kill 50% of individuals. If you're doing a toxicity study of some like pollution in the water, right? You can't test every single concentration. What you do is you may do twofold dilution. So you've got full strength and then 50% and then another 50% and another 50%. And what you're going to do is instead of doing 1,000 different replicates and every decimal point in between, you're only doing 10. And then you look for that spot, those two concentrations where you've killed way too much or you killed way too little, and then you extrapolate to figure out what your 50%. So that's where medians come to. All right. We will pick up with the mode and review central tendency. Actually, we'll finish mode because the mode is just the most common number. Make a frequency table, look at the highest number. So our frequency table example here. The mode is 1. We've got the most grids that have 1. Its utility in biology is minimal. I think you could come up with examples when the mode would be reported, maybe. So if you're doing behavioral types of studies, it's kind of hard to say, well, the average behavior is this. I think what you're actually talking about would be the most common behavior, which would be a mode at that point. All right, we'll look at some of the modes. Modes should be one-peaked, and that's one of our assumptions. If you're normally distributed, you have one peak. You have a single mode. All right, we'll end there. We'll do a quick review of our central tendency on Wednesday, and then we will move to our dispersion, measures of dispersion. All right, we have homework due on Wednesday, so you are free to stay here and work on it. If you want to leave, you can. All right, I'll stay as long as someone's in here working on these stats.
Will you put the RCD back on the screen?
Put RCD back up on the screen? Yes, I will. Which part are you looking for?
The quantile and quartile portion.
The practice part or
Yes.
like the notes? Practice parts? All right, that is all the practice.